Hi everybody, this is our lecture on section 4.1, vector spaces and subspaces. So before we get into it, just a note for your intuition. Keep in mind throughout all discussions pertaining to vector spaces and subspaces, that one, any vector space V is really just Rn in disguise, or not in disguise. A vector space is just another way of talking about Rn, although there's various disguises you can put upon it. 2, every subspace W of V, every subspace W of vector space is span V1 to Vt for some vectors Vt, for V1 to Vt, for some vectors V1 to Vt. So talk about vector spaces gets pretty abstract, okay? But even though it's abstract, okay, if you keep in mind that a vector space is really just Rn in disguise, and every subspace is somehow the span of a collection of vectors, then you'll be a little bit better off. Now, it's not exactly true what I'm saying here. For this class, it's true. Okay. I will mention one example where it's not quite true, but it's far beyond the scope of the course. Okay? All right. So, definition. So, a vector space V is a collection of vectors such that, now, when we say vectors, it's a collection of things which are called vectors. Such that for all u, v, so for all vectors u, v, and w in V, and all scalars s and t, the following are true. And there's nine axioms. 1. U plus V, for every U in V, U plus V is still in V. So when you add together vectors, they're still vectors. U plus V is equal to V plus U. Addition is commutative. 3, addition is associative. U plus V plus W is U plus V plus W. 4, there is a vector 0 in V such that 0 plus V is equal to V plus 0 is equal to V. I guess I don't have to say that. Just 0 plus V is equal to V. We already know it's commutative. Okay, so there's this 0 vector. 5, there is a vector minus v, such that v plus this thing called minus v is the 0 vector. Okay, so addition is closed. In other words, when you add vectors, you get another vector. It's commutative, associative. You have something called 0, and you have negatives of vectors. Okay, so that's the first 5 axioms dealing with addition, and then there's some axioms dealing with scalar multiplication. 6, TV is in V. When you multiply a scalar times V, you get something in V again. 7, S plus T times V is SV plus TV. So you have this type of associativity, or distributivity. You have this type of distributivity. So scalar multiplication distributes over vector addition, and scalar addition distributes over scalar multiplication. And 9, last one, 1, the number 1, scalar 1 times V is just V. So these are the axioms. So, I mean, like I said, it gets kind of abstract, okay? But keep in mind that this is really just another way of talking about Rn. One has to prove that. We're not going to really do it. One has to actually prove that anything that satisfies these 9 axioms is actually, in fact, just Rn. We won't actually do that formally, but that's what it is. Okay? It might be in the book. I actually don't know if they do it in this text. Let's see. So it's a spoiler alert, what I just gave you. But that's okay. Spoiler alerts are good in math. Alright, so for example, one, Rn is a vector space. We've already talked about that before. 2, Pn is equal to the set of all polynomials of degree less than or equal to n. So a0 plus a1x plus a2x squared plus anx to the n, where a1 to an are real numbers. So the set of all polynomials of degree less than or equal to n, right? Because that could be 0, in which case it's not degree n, it's degree something less than that. Right? This is a vector space under the usual notion of addition of polynomials, where you collect like terms for powers of x, and multiplication of a polynomial by a real number, where it distributes over the terms. And clearly this is Pn is just which vector space? R what? Think about it for a moment. So you have this real number, this real number. So this real number in the first spot, this real number in the 0 spot, this real number in the 1 spot, this real number in the 2 spot, this real number in the n spot. I mean, it's just like doing this. Because when you're going to add like powers of x. So you would add polynomials component-wise. And when you multiply by a right? You're going to multiply all of these coefficients by that scalar. So it's really just R what? Not Rn, it's Rn plus 1 in disguise, right? Because when you start at 0 and you go to n, that's n plus 1 numbers, not n numbers, right? 1 to n is n numbers. 0 to n is n plus 1 numbers. Anyway, so clearly this is just Rn plus 1 in disguise. Not a very good disguise. Not that there's not a reason to ever do that, to put on this disguise. I mean, there is a reason to put on the disguise. I mean, you can do calculus with polynomials, right? So, combining the calculus and the linear algebra, it really gives you something with some real, meat to it. So there's really something to study there. So there is a reason for doing that. In this class, there isn't really, but in subsequent types of math, there is. Partial differential equations, real variables. Where else would you do with that? And combinatorics. There's this place for that as well. Okay. Third example, and here's one that's actually not Rn. It is in a way, it's R infinity, but it's a little something different. And this is really an extension of number 2, is the set of all continuous functions on the real number, on the real line. This is a vector space as well, because when you add continuous functions, they stay continuous. Right? When you multiply a continuous function by a scalar, it's still continuous. And that's essentially gives you all the thing, and addition is commutative within the real numbers, so on and so forth. So that's really an extension of number 2, a very big extension, and you can do calculus on the set of continuous functions on the real numbers. Okay. So that's all I'm going to say about that. I'm not going to say any more about it. If you take partial differential equations, they'll definitely talk about that stuff some more. All right, subspaces. So a subset of vectors, W, of vectors in vector space V is a subspace when W itself is a vector space. So it's a vector space contained within a larger space. So 2 and 3. Polynomials are continuous functions, right? But not all continuous functions are polynomials, right? So actually Pn is a subset, number 2 here is a subset of number 3, right? Continuous functions that aren't polynomials are like sine x, cosine x. Those are continuous, but not polynomials. All right. So a subset W of vectors in vector space V is a subspace when W itself is a vector space. And the theorem is as follows, which we won't prove, but I'll give you a quick explanation. So a subset, actually let me call it S. When S itself is a vector space. So a subset S of vector space V is a subspace when S satisfies the following. So, not all the axioms for vector spaces. Not all the axioms for vector spaces. Right? The axioms for vector spaces come in 2 varieties. things for all vectors and all scalars, and things talking about the existence of vectors and scalars. So commutativity is for all vectors. So commutativity holds for any subset of vectors. Or sorry, this one. Commutativity, right? Every pair of vectors in V commute, so every pair of vectors in S commute. They must because they're in V. Every triple of vectors is associative in V, so it's got to be in S as well because S includes everything, because everything in S is included within V. This one here, distributivity, that's again for everything, that's for everything, that's for everything. So the only ones that talk about existence are 1, 4, and 1, 4, and 6. Actually, 5 does too, but you don't need it. Okay, just 1, 4, and 6. When S satisfies the following, right? U plus V is an element of S for all U and V in S. 4, 0 is in S. And 6, T, V is in S for every V in S and scalar T. So just those 3 things are necessary for showing that something is a subspace of V. A subset is a subspace. Okay, so the proof is really what I just gave you, except for this thing about negatives. But, you know, I don't want to spend time on that. It's not really that interesting for this course. All right. Example. One example. So let V be a vector space and vectors V1 to V, let's see, T in V. Then the span of V1 to Vt is a subspace of V, period. Okay, and we call this subspace, and this one we're going to prove. The space spanned by or generated by V1 to Vt. Remember what span is. Span is the set of linear combinations of the indicated vectors. Okay, so let's actually prove that. Okay, we just have to show 3 things. Every pair of vectors in the span here is, when you add them, it stays in the span. The 0 is in the span. And when you multiply a scalar times something in the span, it's in the span. Okay, so take 2 vectors in the span. Now, every vector in the span is, by definition, a linear combination. So by definition, these are of the form. So we'll say C1 V1 plus CT VT, and we'll say D1 V1 plus DT VT. All right? So when you add them, so this is number 1. if I add those guys, right, all I have to do is just combine like terms with like terms for v, vectors v. So this plus this is just equal to, right, well, it's going to be C1v1 plus D1v1 plus CTVT plus DTVT, and then you can factor out the v, because in a vector space V you have that distributive property. C1 plus D1 V1 plus CT plus VT DT, which by definition, which is, a linear combination, or VT, CDV, which is a linear combination from that span, V1 to VT. So that's number one. I took two things in the subspace, I added them, it's still in the subspace. Right? Clearly 0 is in the subspace. V1 to VT, because, right, 0 V, scalar 0 V1 plus scalar 0 times VT, right, is equal to 0. Right, the 0 vector. Right, that's equal to 0 vector. Each one is the 0 vector in V, which is equal to the 0 vector. And then 3, if you take a linear combination and you take a scalar S, this is equal to, just do the distribution, S D1 times V1 plus S dt times Vt, which is in span V1 to Vt. Okay? So there you go. So that's always a subspace of your vector space. And a particular example of this that we've seen of this kind of thing, let A be a matrix, n by n matrix. Okay, let A be an n by n matrix. The set of all vectors x such that A times x is equal to 0, right? We've talked about this, right? Is a span of some collection of vectors. Of 0 to n vectors. Maybe 0 vectors, maybe 1 vector, 2 vector, 3 vectors, so on and so forth. Okay, so that's a subspace. Of Rn. It's called the null space of A. So actually it doesn't have to be n by n. It can be R by n. Right, any R by n matrix. Okay, so that's a particular example, a very important example, which we will be talking about. Okay, and that's the lecture for this section.